Okay. So, chapter 10 is the real organic chemistry. Technically, this is the first part of this class. I added in chapter 3 and 4 because I felt like it would be a good warm up before we get to chapter 10. Chapter 10, we're going over what organic compounds are, the characteristic features. So, some of the things we go over in chapter 10, it will feel like we are back in chapter 3 and chapter 4. That was intentional, okay? So, I'm going to go straight into organic chemistry. Organic chemistry is a special area in chemistry where we talk about compounds that have or contain the element carbon. So, in the world outside of organic chemistry, they refer to natural things as organic, organic milk or organic chickens or organic whatever. They're talking about natural things. In the world of chemistry, organic means carbon and its compounds. Okay? So, that's the context. Organic compounds are present in many substances and that therefore affect the world around us. When you think about clothes, you have foods, medicine, gasoline, and soaps. Can you imagine that? All of these have an organic component to it. So with our clothes, things like polyester. Polyester just means many ester. We'll talk about that later on. You have foods, anything that's greasy and tasty, organic compounds. You got medicine, gasoline, soap. So we'll talk about this down the road. So the way this chemistry works is an application component to it. Okay? So there's a certain characteristic feature of organic compounds. Organic compounds are molecular compounds. Okay? An example of organic compound is called methane. And methane is the gas that you have at home. If you have gas in your house, natural gas, that gas is most likely methane. And methane is an example of an organic compound. We see right here. The other example we see here is ethylene. With ethylene, this is essentially polyethylene. This is the plastic that's used to make these containers right here. And then the plastic bags they ask you to recycle, those are all polyethylene, sometimes called polythene bag or polyethylene bag. So we can see the application of organic compounds all around. Let me make sure I have the most recent message right here, okay? Okay, so now we're getting to the organic compounds itself. All organic compounds contain carbon. They have to contain carbon to be an organic compound. Okay? So they can contain carbon. Sometimes it's carbon and hydrogen. So at least they have carbon and hydrogen. Sometimes they have carbon only and other elements. But the base elements are carbon and hydrogen. They may have additional elements such as chlorine, oxygen, nitrogen. When organic compounds have carbon and hydrogen only, they're called hydrocarbon. So at some point in the PowerPoint slide, this will be defined. Hydro for the hydrogen, carbon for the carbon. So essentially, hydrocarbon, organic compound that only has hydrogen and carbon. Okay? And then the collective name, there's a lot of collective names in this section here. The collective name of the elements that are not hydrogen or carbon are called heteroatoms. So if you want to refer to them as a group, they say, oh, those heteroatoms, the others, the ones that are not hydrogen or carbon. Okay? We talked about this in the previous chapter. Carbon always has 4 bonds. Remember the Lewis dot structure? Oh, I don't have a periodic table in here, but carbon is in group 4, right? Being in group 4, it has 4 dots around it. And we said in the previous chapter, the number of unpaired electrons equal the number of bonds. So every time you see, at least for you guys this class, because this is a non-majors class, every time you see carbon, it will be surrounded by 4 bonds to match with the number of unpaired electrons. So they show that to you here. Let me zoom this in. You can see the carbon here with 4 dots. Okay? So those 4 dots came from carbon. And of course, hydrogen is in group 1. Let me use a different color for hydrogen. Hydrogen is in group 1, so it has 1 dot. So each of these hydrogens in here came in with their 1 dot. Okay, and the dot here represents the electron. So this is kind of a review of what we saw before. So in making the compound, it takes 2 electrons to make 1 bond. So these 2 electrons just get translated into a single bond. So you see the bond here, the bond here, the bond here, and the bond here, right? So there we have methane. And essentially this is how they got together. So from here, what is that takeaway lesson? Hydrogen, because it has 1 dot, will always have 1 bond. So I say here, always 1 bond. What about carbon? Our take home lesson. Carbon will always have 4 bonds. Now, the bonds can be grouped together differently, but it will always have 4 bonds. Okay? So before we continue, this is a quick check. And they're asking you here, which of the following compounds, I guess the list, contains only organic compounds, right? So we said before, at this point, if you want, you can feel free to answer. That's fine. We said organic compounds have at least carbon and hydrogen, right? It can have a third element, it can have a fourth element, but at least it has to have carbon and hydrogen. You can say and others, right? So we're going through. This has carbon, it has hydrogen, and the other element is oxygen. This one here is missing a carbon. It has a hydrogen, but there's no carbon. This one doesn't have either. So definitely A is not the answer. What about B? Carbon, hydrogen, check. Carbon, hydrogen, carbon again. 2 oxygens, hydrogen. Okay, this fulfills that criteria. Carbon, hydrogen, hydrogen, oxygen. Oh, so I'm thinking this is one of the answer choices. Let me check to make sure there's only one answer. This is not carbon, this is not carbon. So we need carbon, hydrogen, and other elements. So not that, making this not the choice. Let's see. This one here, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, chlorine. Chlorine works. So the other elements, by the way, over here tend to be nonmetals. Okay. Oh, this is a metal. Potassium, no. So no to this, therefore no to that. So the only possible answer here that has organic compounds only is B. Okay. Any questions about that? If I answer a question and you still have a question, please feel free to ask, you know, because you guys are kind of here to slow me down so I can slow down and address things over and over again if necessary. Okay. Okay, so we talked about carbon having 4 bonds. Now, sometimes the 4 bonds can be, in singles like this right here with this group called ethane. We haven't learned nomenclature yet, which is to name compounds, but eth stands for, so this prefix here, ETH, stands for 2 carbons. Okay, so every time you see SSS, it stands for 2 carbons. And then A and E is just saying 2 carbons from alkane. Or I can write this differently and say alkane, this is a family of organic compounds with 2 carbons. So when we get to the naming part, we will go over this in detail. We'll go over it step by step by step. But that's what this is, alkane with 2 carbons. This one also has an S and ends with ene. And so this one is from the family alkene with 2 carbons. Okay, and we'll talk about this group down the road. For right now, once again, we're just introducing this. This one here actually has a common name, acetylene. It's technically ethine. That's the technical name. S again is 2 carbons. Y and E is triple bonds. So here we have alkyne with 2 carbons right there. Okay, so let's zoom back and see right here. Right, we have 2 carbons here in the middle. Both carbons are your central atoms. We have 2 carbons here in the middle, and you see they're holding a double bond. So we'll learn later on that Organic compounds that have double bonds are usually called alkenes. And you can see here how the carbons are holding the two bonds right in the middle. Here, the two carbons are holding a triple bond. We have three bonds right here, and this is called alkyne. So, with the alkane is a single bond, alkene, double bond, alkyne, triple bond. Okay. Now, the focus of this was just to say that, hey, notice the carbon can be surrounded by four single bonds, as in the alkanes, like we've seen that, or the bonds can be grouped together where two are grouped together and then the last two are separate, as in the alkenes. Or you can have a case where three bonds are grouped together, as in the alkynes. Okay? But all three carbons are surrounded by four bonds. The alkane, four single bonds. Alkene, two single bonds, one double bonds. Alkyne, one single bond, and then one triple bond. Any question about that? There's a lot of patterns to this class. When I was learning this at first, I was completely overwhelmed. I was like, what in the world is this? It's very different. But once I figured out it's like a puzzle, I was like, oh, okay. So I'm always looking for connections and themes and stuff like that as I look at this, right? So when we see carbon triple bond, we know it's an alkyne. Carbon double bond carbon, we know it's an alkene. Carbon single bond carbon, we know it's an alkane, right? So we're establishing kind of ground rules. Okay. Meanwhile, maintaining four bonds around carbon. Okay. As we're learning types here, we're told some organic compounds exist as chains of atoms, acyclic. Now we're kind of going into those Latin words, right? Where if you add a in front of a word, that's like not that word, right? So acyclic is definitely not cyclic. So this is more as a student, I used to have those questions. Why not just call it linear? It isn't exactly linear, even though Lewis structure draws it like it's a line. It's just not circular or cyclic. Okay? So in this case here, they're showing you propane. This is an alkane. One of the ways you can tell it's an alkane, you see how alkanes end with A-N-E? This ends with A-N-E. So the prop here stands for three carbons. So we have an alkane with three carbons. Once again, we haven't learned names. We haven't learned naming yet, but I want to kind of introduce this. So we're looking at propane right here. And then this is called acyclic. Why is it called acyclic? You see how the carbons are attached to each other? It's back to back to back. Like the first carbon is on the left, the second in the middle, the third on the right. And you see how carbon number one doesn't connect to carbon number three? Carbon number one is all the way to the left, carbon number three is all the way to the right. So they're kind of in series, right? Carbon one, carbon two, carbon three. And then around the carbons, like we just learned, we have four bonds total around each carbon. One, two, three, four. One, two, three, four, right? One, two, three, four. And then on the end of each bond, you have a hydrogen. Over here, this is called cyclic. It doesn't even look round. It's not really about having a round shape. It's just that the first carbon connects to the last one. Let's assume this carbon on the left is carbon number one. The top one is carbon number two. The one on the right is carbon number three. You see how one connects to two, then two to three, then three back to one. And so in the middle here, we're forming a triangle, so sort of a geometric shape. This is called cyclic. And so the name describes it. I went from sort of hating this class to falling in love with it. Okay, I went from it went like from one extreme end to another, right? Because I was like, I can't figure it out. Then once I figure it out, I'm like, I love it so much. Extreme emotions, right? Because I'm like, okay, I see. It's kind of like a charades thing, even though I'm not very good at charades, where the name describes the structure. So now here in the name, we're bringing another element to the name, cyclo, meaning that connect the ends, right? Cyclo, so it's sort of a cyclic compound. Prop, three carbons. Ane, alkane. right? Very systematic. So it's not just a name, Bob. No, it's systematic. The name sort of describes the structure, right? So cyclo is like cyclic, or should I say geometric, right? The one end connects to the other. There's three carbons in the middle total, and then this is an alkane, meaning that all the carbons are connected via a single bond. So alkane means here carbons uh, bonded via single bond. Okay. Any questions about this? Okay. So we're moving, we're going on. Okay. So here I already mentioned heteroatoms, so I won't say any more about this. I won't even go through this list. This is a long list of just Lewis structures, right, for the different elements. We already went over that in the assignment I gave you guys earlier. These are a few of the heteroatoms. Please notice they're all non-metals, right? They're all nonmetals. So the other nonmetal in the periodic table, if they're added to carbon, hydrogen, they're called the heteroatoms. So real quick here, we're told that regardless of the heteroatom, all these heteroatoms here have to essentially have octet. And depending on the group position, they're getting to octet via different means. So let me see. While I'm here, I can list this real quick. Let's go through nitrogen, oxygen, and then I'll do fluorine. And fluorine represents all of these because remember, fluorine, chlorine, bromine, and iodine, they're in the same group. So whatever works for fluorine as far as the bonding is concerned, works for the other ones. Okay. Nitrogen is in group 5, oxygen group 6, fluorine group 7. So I'm going to draw 5 dots around nitrogen. I'll start with up. It doesn't matter where you start. 1, 2, 3, 4, 5. So from nitrogen, I need space. From nitrogen, I can see that nitrogen will have 3 bonds, right? 2 lone pairs based on its Lewis dot structure. Okay, let me work on oxygen. Oxygen has 6 dots, right? Group 6. 1, 2, 3, 4, 5, 6. Okay, so oxygen will have 2 bonds, 2 lone pairs, right? Let me find a space for fluorine. I'll put fluorine right here. It will work. Fluorine has 7 dots. 1, 2, 3, 4, 5, 6, 7. Okay, so fluorine will have 1 bond and 3 lone pairs. The bonding pattern we expect ties back to that Lewis structure that you guys were working on before. Okay, so that's why we're working on that stuff in chapter 3, is to prepare us for this time right now. So knowing that they kind of go over this is a normal bonding pattern. Hydrogen always has 1 bond, never lone pairs. In the video, the other video I shot, I said never, never, never try to put dots around hydrogen because you feel sorry for it. No, hydrogen, this is a bonding pattern. It will always have this bond and it never varies from that. With carbon, you have 4 bonds. We know that the bonds can be grouped together, right? But they have to be 4 bonds. Nitrogen has 3 bonds. Yeah, these bonds can be grouped together, but it has to be 3 bonds and then 1 lone pair of electrons. Oxygen, 2 bonds. Can they be grouped together? Yes. And then 2 dots. Okay. Hydrogen, halogen. Halogen is group 7. So that means it's fluorine, chlorine, bromine, iodine. You have 1 bond here, 3 lone pairs. That's 3 lone pairs that have an extra dot. Okay, so now that we've seen that here, real quick, they're showing you oxygen with the bonds apart, right? 2 bonds, 2 lone pairs, and then oxygen with the bonds grouped together. Okay, it still has 2 bonds and 2 lone pairs, and that's how this oxygen gets to octet. So I'm going to go ahead and move on and start with this question right here. Here we're told, so we're continuing the same theme. Draw in all the hydrogens and the lone pairs in each compound. So, I mean, you can go ahead and fill in the stuff, but what I want to do is I want to just remember what I did, right? Chlorine is in group 7, so I got 1, 2, 3, 4, 5, 6, 7. So that 1 becomes a bond, and then let's see. Carbon is in group 4, 1, 2, 3, 4, like that. And then what else do I have here? Oxygen is in group 6. 1, 2, 3, 4, 5, 6. So you have a bond here and a bond here. What else do I have? Nitrogen. I'll write that over here. Group 5. So you see, you want to make sure you know these, right? 1, 2, 3, 4, 5. I'm making a bond out of the single dots. Okay. So the goal is to repeat this bonding patterns in these structures right here. So I'm going to draw in all the missing components, right? For chlorine, I do have my single bond here. I'm missing 3 lone pairs. 1, 2, 3. Do I have any other chlorine here? No. Okay, with carbon, I have to have 4 bonds. On this carbon in the middle, I only have 2 bonds, right? So I'm missing a bond here and missing a bond here. The carbon on the left, this bond belongs to both the carbons equally. So this carbon on the left has this bond on the right, bond on the left. It's missing 2 bonds, so up and down, right? Technically, it was missing how many originally? It was missing 3. Okay, so 1, 2, 3. I have to add those to make 4. Okay, so at the end of each bond, I have to put in a hydrogen. Here, 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 here. Because it says draw in all the hydrogens. I have to have the bonds first so I can put in the hydrogens, right? Okay. So for oxygen, I know oxygen has to have 2 bonds. Okay, the 2 bonds are over here. Check. And then 2 lone pairs. So I have to add what's missing. A lone pair there and a lone pair there. Carbon has to be surrounded by 4 bonds. Okay. The carbon here in the middle already has 2 bonds. There's a bond missing. I'll add that. 2 bonds on the right, 1 bond on the left. It has 3 bonds. It's just missing 1 bond. You all see that? The carbon on the left is missing 3 bonds. It already had 1. I just needed to add 3 more. On the end of each of these, I'll put a hydrogen. Now work on this one here. Nitrogen. What's the bonding pattern? Nitrogen has 3 bonds, 1 lone pair. So over here, I got 1, 2. I need to draw 1 more. Then I need to add a lone pair, dot, dot. Carbon needs to have 4. This carbon in the middle has 3, is missing 1. The one on the end, on the left, has 1, is missing 3. 1, 2, 3. So I put H here, I put H here, I put H here, I put H here, I put H here. Okay? Once again, if you have any questions, don't wait for me to stop talking. You can type it in there, and then as soon as I recognize it, I will address the questions, okay? So for this one, I will skip over the ones that are kind of similar to what we've covered before and do the unique ones. Okay. Now I'm looking at this saying, what is unique? I feel like everything is unique, okay? I'll do this one here, this one here. Yeah. Okay. I guess in this one here. Okay, that third one. Okay. So I'll start from this one here. I need to make sure each carbon is surrounded by 4 bonds, right? I'm going to add 3 to this one, add 3 to this one, add a 4th to this, right? Just add 1 to that. Now each carbon is surrounded by 4 bonds. The oxygen has to be surrounded by 2 bonds. So I'm going to put a bond here and then 2 lone pairs, dot, 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 dot. I guess. Okay. At the end of each bond, I'm going to bring in a hydrogen. Hydrogen, 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 hydrogen. There, 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 there. Okay. I don't even have room for the top one now. Okay. When you're looking at this at home in your own spare time, you can pause the video. That's the great thing about videos, right? You can pause it, you can rewind it, you can do all that stuff. So for that reason, I'm going to erase this bottom part because I need the space. Okay. I can make these short and write this smaller. Okay. So I'm going to look at this right here. The carbon is missing 3 bonds. The nitrogen is missing 1 bond and 1 lone pair. This carbon is not missing anything. It's got all 4 bonds. This is missing 3 bonds. The oxygen has its 2 bonds, but it's missing 2 lone pairs right there. Okay? So now I can go through and put H, 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 H. Right? Okay. Over here, let's see. Yeah, we have to follow the rules, right? This oxygen has 2 bonds right here. Even though it's in cyclical form, it has 2 bonds. It's just missing 2 lone pairs. This carbon has a bond here and a bond here, is missing two bonds. This carbon here is missing two bonds. So all I have to do is bring in the H here, the H here, the H here, the H here. I'll just share with you some of my experiences. Sometimes it's hard to follow the rules when the circumstance appears different, right? Because in this case here, the cyclic compound completely different, but you're following the rules. Carbon has to be surrounded by four bonds, and oxygen two bonds, two lone pairs. So even though the condition looks different, you want to stick with the rules. I had a student once tell me, I don't follow the rules. I'm like, well, I don't know what to say. I don't know what to say. That's what I said, and I walked away. Okay, so now we're moving on. We're getting closer to the part where we can work on isomers, right? We're kind of getting closer. Okay, here we're learning how to deal with condensed structures, okay? The context here is chemists are lazy. At some point, I decided in my life, chemists are just lazy. They do a lot of chemistry, they get tired of writing. And you know, the more you write, there's a higher chance of making mistakes, right? We're not dealing with numbers here, but even with writing these molecules can get very big. They can have 100 carbons. So it gets tedious. So they came up with a condensed structure where if a pattern repeats over and over and over again, you can shorten it, right? So here we're told a condensed structure. In a condensed structure, all of the atoms are drawn in, but the bond lines between the atoms and the lone pairs on heteroatoms are generally omitted. Okay, so in this example here, they drew the Lewis structure out. And then from the Lewis structure, we get a condensed form. So let me see, can I squeeze down here? Yeah. So you have this, and if possible, you want to draw this around central atoms. Okay. And I'm going to highlight which they are, or which carbons are central atoms. For the most part, if you have a carbon, it's a central atom. A hydrogen is never a central atom, right? So this is a central atom. And you're going to draw your central atom. So I have one here, I have another here, I have another here, and I have another here. So starting with the first central atom, this one here, you write your carbon, and then you look at the other atoms surrounding your carbon that are not central. So this hydrogen, that hydrogen, that hydrogen. Some books write the hydrogen on the left here, and they put 3. Some books write it on the right. It doesn't matter. The point here is the first carbon is surrounded by 3 hydrogens, meaning that these 3 hydrogens belong to the first carbon and they're bonded to it. Okay? Let me see if I can just go back. Yeah. Okay. Then you don't have to draw the bond that connects all the central atoms here. You can just draw the second carbon, this second carbon right here. The second carbon is bonded to 2 hydrogens that are not central. So you write here H2, right? And the third carbon right here is bonded to 2 hydrogens that are not central. So that would be H2. Then finally, our fourth carbon here is bonded to 3 hydrogens that are not central, H3. So essentially, this is central, this is central, this is central, this is central. The hydrogens are not. Okay? So hopefully you see that. As we are working on this, we're kind of dealing with isomers, right? We're sort of dealing with isomers. So actually what I'm going to do here is when I get done with this, I will go over the isomer part because I feel like it sort of ties into this. It can tie into this. Okay, with this one here, it takes a while to know how to do this properly. I know we don't have a lot of time, so I'm going to do my best with this. Here, let me tell you the centrals I see, the central atoms. I see this one here. I see this one. I see this, this, and this, right? And so what you can do here then is just write your carbons. Let me write it with red. 1, 2, 3, 4. And then you have the one that's up here, right? The first one here is surrounded by 3 hydrogens. The second one here only has 1 hydrogen. You don't want to write this part here as part of it. You could, but I'm trying to keep it simple. So one hydrogen here, and then the top part is surrounded by these three hydrogens, so CH3. This one here, H2, and this last one here, CH3. You can condense it even further, but for right now, I'll leave it that simple. Okay? With this one here, since this is condensed and we're condensing it even further. To make this even shorter, instead of having to write CH2 twice, you see that CH2, the middle part looks exactly the same. Wait, hold on a second. I'm using the wrong thing. What they did here was combine these two. So they say essentially CH2 written twice gives you that structure right there. Okay? To kind of shorten it. And then here, because you have the same group on the top and on the left, they combine those two and put them in parentheses like that. Okay, I know it gets a little wonky here, so I'm actually going to work out because I think we do have some problems here that we have to work on. Yes, right there. I hope I have enough space. Okay, in this one here, as you can see, I'm going to try to make it simple and I'm going to condense these. So these are my central carbons, 1, 2, 3, 4, 5, right? And then I have 2 here, 1, 2. So let me see if I can draw this here. 1, 2, 3, 4, 5. Then on the second carbon, this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. On my second carbon, I have another carbon sticking out here. On my fourth carbon, I have another carbon sticking out here. The first one is surrounded by 3 hydrogens, so I'm going to write here H3. Second one only has 1 hydrogen, H. Third one has a hydrogen up and down, H2. Fourth only has 1 hydrogen, H. Fifth has 3 hydrogens, H3. This top one here is surrounded by 3 hydrogens, H3. 3 from here, H3. And that's my condensed structure. Okay. Now, with this one here, I'm going to condense it more than I normally would. I'm going to condense this twice. Okay. Just so you can see how it works. You don't have to do it that way when they're asking you questions that you have to draw. Thank you, Elizabeth. That's what I'm usually trying to get you guys to work with me. There's something magical about us, yeah, working together. It's kind of like a puzzle. And then think about lazy people trying to make life easy for themselves so they don't have to write over and over and over again. Right. Thank you for the feedback. Okay, so I'm going to do a two-step condensation, making this more condensed, right? One where this is the central atoms, right? And then you have these poking up on top and on the bottom. So when I wrote this, I thought I had a lot of space. Okay, so 1, 2, 3, 4. Okay, I feel like I don't have enough space. Let me make this tip a little smaller. Okay, there. 1, 2, 3, 4. Okay, so, and then this is 1, 2, 3, 4. There's a lot of counting here. So on carbon 3, I have the top one and the bottom one, right? A carbon here and a carbon here. Okay, this first one here, 1, 2, 3. So CH3. The second one, CH2. Okay, top one, CH3. Bottom one, CH2. The one on the right, oh, there's no hydrogen here. Okay. The one on the right, 1, 2, 3, CH, oops, wrong thing. CH3. Okay. So here's the thing. I don't have a lot of room, so I scrunch these numbers. CH3. Okay. So do you see how there's a CH3 here and here and here, and all these 3 CH3s are bonded to that carbon? We are about to condense this one more step. Okay. Let me see if I can make this bigger because, yeah, I'm going to condense this one more step. So I'm going to leave this as is, leave that as is. So it's going to be CH3, CH2. Then for my C, this C is surrounded by this group, that group, and that group. So I'm going to put those inside a parenthesis and say this carbon has 3 CH3. threes. So I condense it the first step, and I condense the condensed even further, right? So as long as the same group surrounds the same central atom, they just condense it. The goal is, I should use the term efficient. One of my class told me, "You're being efficient." I said, "Sure, sure, we'll go with that. Efficient versus lazy," right? So because these three groups were attached to the same carbon, they're saying these three groups attached to the same carbon, these two hydrogens to that carbon, these three hydrogens to that carbon, right? Okay. And then this one here, when it comes to heteroatoms, it's hard to condense it, right? So let me see. With this one here, once again, this carbon, 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 central one oxygen, carbon. Let's see how we'll deal with this. This is our central atom. So carbon, 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 oxygen, carbon. Okay. The first carbon has these three groups, CH3. Second carbon has these two groups, CH2. Third carbon has those two groups, CH2. Oxygen has dots. We're not showing dots here. The dots are implied. Then we'll skip over that to the carbon. The carbon here has two hydrogens, and then the chlorine is right here. So they can write this group up here like that. You cannot consolidate the chlorine with the hydrogen because it's the different elements. All you do with the ones that have the lone pairs is leave out the lone pairs because it's kind of like a lazy formula. Okay. Then from this one here, let's see, we'll do that one too. Once again, my central ones are C, C, O, C, C, O. Okay. So I'm going to write here C, C, O, C, C, O. Okay, for this C, I have those three hydrogens, right? That right there. Two hydrogens. Oxygen has nothing. Then this carbon has two hydrogens. This carbon has two hydrogens. And then this oxygen has a hydrogen, so you put it right here. Okay? Yeah, excuse my handwriting, but that, yeah, that's the condensed form. So from here, they can have you spread it out and, so what I'm going to do right now, I'm going to pick the tough ones to work on those. As I'm looking, I'm like, there's a lot of tough ones here. Let me see. I definitely want to work on number 5. Number 5, number 4, and number 3. How about that? Okay, because I'm trying to get through these faster. I have so many questions here just to give you guys more practice. Okay, so the first one here, so I'm going to be using the space I have. C is my central atom, C, and then this is chlorine. So I guess I have two central atoms. Remember, if you have a carbon, this is organic chemistry, all about carbon, right? If you have a carbon, most likely the carbon is a central atom. So I'm working on C right now. This C is surrounded by 3 H's, right? So I'm going to draw 4 bonds around it. This is my first carbon. Second carbon, I'm going to draw 4 bonds around it. I just realized I don't have enough space. Okay, hold on. 2 carbons. Left one has 4 bonds. Right one has 4 bonds. They share the bond in the middle. Okay. The left one is surrounded by 3 hydrogens. 1, 2, 3. The right one is surrounded by 3 chlorines. 1, 2, 3. Don't forget dot, 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 dot. You have to make octets of the elements that are not hydrogen. Make an octet. Bring in the lone pairs. So this is that. Okay. Can I do this over here? Let me try to open it at a page. So I'm going to copy this in the next page because it gets difficult. Oops. What am I doing? Oh, I forgot they have new features. Sorry. I get excited over little things. Let me copy this right here and put this right here. Okay, so we're going to be working on this one here. I got a carbon. It says 4. 4? Okay. So there's going to be 1, 2, 3, 4, and then there's a 5th one here, a 5th one, and then this one here is 2. Oh, no, but these are CH3. Okay, so here's the thing. Before I continue this, so you can follow along what I'm doing, I want you guys to be with me versus behind me. CH3s tend to be corner carbons. Okay? They tend to be corner carbons, the ones that have 3 hydrogens. You probably have been seeing it, but I want you to recognize that when you have 3 groups or 3 hydrogens attached to a carbon, that carbon is a corner carbon. When the carbon has got 2 groups like CH2 or just 2 bonds or something, 2 groups, it's a middle carbon. Okay, so that's an easier way to kind of notice this, a middle carbon. So as I'm looking at these, right, I can judge. This is a corner. Like when I say corner, I mean end. Okay, my bad. Let me say this properly. End carbon, right? As in it can be the beginning, can be the end, whatever. So this is an end carbon. These are CH3. So they're end carbon, not middle carbons. Middle carbons are CH2s. So when I'm writing this out, I'm going to write it like this. CH3 is first. That takes care of these. Then I have 4 CH2s. They'll be next to this. CH2, 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 CH2. 4. I'm done with this part. Then comes a CH. Okay, I'm done with that part. Then the CH3, these are end carbons, right? So if I want, I can put one on here on this end, but I can't put the other one on the end because both have to be end carbons. So what I can do is I can put one on the end and I can put the other one on the end right here because CH3s are end carbons. I know, I know. It's like a puzzle, right? You'll be seeing this a lot, so I know it's a fast class. You'll be seeing this a lot and it'll become more familiar. Just when you're doing this class, make sure you write stuff down. I'm learning some new things in my life right now. When it gets overwhelming, I'm like, hold on a second. Let me get my notebook down out and then I write it down. And what that does for me, it slows my brain down and gives my brain a chance to catch up. Sometimes things go too fast and I'm like, okay, hold on a second. And then weirdly enough, when I do that, it actually makes a lot more sense. So the CH3s are end carbons, or they can be like a dangling end, a branched carbon, whatever, but they're never in the middle. Okay. So they said that we should draw a complete structure. Okay. So here I can take this. I'm going to show all the bonds. 1, 2, 3, 4, 5, 6, 7. 7 carbons, right? 1, 2, 3, 4, 5, 6, 7. Make sure you have 4 bonds around each. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. And then on the second one from the left, we have a carbon here. There. So you bring in your hydrogens. You see how it works out? I did that part. 1 hydrogen. You see how there's only room for 1 more hydrogen. That part is done. 3 hydrogens. This part is done. 2 hydrogens. That part is done. 2 hydrogens up and down. That part is done. 2 hydrogens here. This part is done. 2 hydrogens here. This part is done. 3 hydrogens here. Done. Okay, I spread this out some more and I spread this out even more so you can see all the bonds and everything. Okay, so this is done. I'll do this last one. Let me copy and paste. Come on. Oh, by the way, just in case you're wondering what app I'm using, they're not paying me. This is not advertising. I'm using Notability app. And earlier I tried to record it right here, only I didn't realize it was only recording the audio, not the video. So when I posted the lab video, it said lab video and you guys clicked on it, it was only a document. I didn't realize until I looked today and I was like, no, this is not what I wanted. Okay. Okay, this is our last one right here. So I have, let's see. Oh, see end pieces, right? End pieces. So I have 2 end pieces. So I'm going to say CH3, that's one end. The next one cannot be attached to this. So I'm going to draw this carbon and attach the next one to this, CH3. So these two have to be, like one has to be on the end and the other one has to be attached to the carbon inside. So this is done. CH2, that is done. NH2. Okay, so I'm going to spread this out even more. I'll do it over here. This carbon right here, that carbon, the nitrogen, and then the carbon down here. Okay, so 4 bonds. 1, 2, 3. I should have put this a little bit higher. I'm realizing that after the fact. Okay, this should work over there. 1, 2, 3. 1, 2, 3, 4. Each carbon now has 4 bonds. Nitrogen has 3 bonds and 1 lone pair. You see that? Okay. Oh, now I fill in my hydrogens. 1, 2, 3 hydrogens takes care of that. This first carbon has 3 hydrogens. You see how it all works out, takes care of that. This carbon needs 1 more hydrogen, that's it, takes care of that. This carbon needs 2 hydrogen, 1 on top, 1 on the bottom, takes care of that. This nitrogen needs 2 hydrogen, one right here, 1 right there, takes care of that. Okay. So I'm not going to go over every one, but I wanted to go over the hardest one so you can see how it works out. Okay, so before we do skeletal, you asked me about isomers. So let me see. I think, let me do pentane. So while we're here, right? I haven't forgotten. Isomers of pentane. Okay, so pent means 5, ane means alkane. So an alkane that has 5 carbons. Okay, so I'll start with the first one. The first one usually is 5 carbons back to back, like in a line, right? So we have 1, 2, 3, 4, 5. And because it's an alkane, all the bonds have to be single bonds. So single bond, single bond, single bond, single bond, single bond. Make sure there are 4 bonds around each carbon, right? And now fill in the hydrogen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the formula for this pentane is carbon, we have 5 of them. Hydrogen, we have 12 of them. Okay? Now, what was I doing again? Oh, yeah, isomers. So this is the first isomer, the one where the carbons are in series, right? Back to back to back to back. The easiest way to get the next isomer is make the longest. So this is called the longest continuous chain. You see from the first one, they're lined up like ducks, back to back to back, continuous chain. The easiest way to make the isomer is by shortening the chain by 1 carbon. Okay? So since I have 5 carbons in series back to back, I'm gonna bring in a 4 carbon one and mess with that. Now, let me tell you what is not an isomer. With the 4 carbons as your longest continuous chain, you can't just bring one here and say this is a completely different compound. Imagine you had pearls, right? Or a necklace or whatever. And then for this bottom one, all you did was branch this. You kind of move it to the side and say, this is a completely different chain. I'm like, no, it's not. It's the same chain. All you have to do is put it back like this, right? So if you bend the end of the longest chain, it doesn't make a different compound. It just makes a bent version of the original compound. What you want is to completely get a different compound. And what I mean by that, as far as the chain analogy is concerned, is this is one chain you have. This is another chain that you have where it has what is that thing called? Charms on it. Okay, so these are considered different because this first one is very long with no charms. The second one has little trinkets hanging off of it, so they're 2 different ones. Okay, so as you're making your isomer, you're trying to shorten the longest chain and then hang the pieces of the carbon that came off the longest chain like little charms on the bracelet. I don't have one of those, but I have friends who have that, and they buy the little charms. So imagine the carbon that's broken. So let me go ahead and go back to this carbon right here. I used to have 5 carbons, right, in series like that. And then I took 1 carbon off, and you can only attach that carbon to the middle ones for it to count as a new compound. If you attach it to the first one, it's still the same compound. So either here or here, okay? I'll go with the left. So the carbon that broke off goes on the left. Now fill in the bonds. 1, 2, 3, 4. Make sure you have 4. So you can see now this looks like a shorter chain with a piece of carbon hanging on the side like a leaf or a charm bracelet, right? And remember, if it's attached to the first one, it's the same as this, because remember how we said these have free rotation? That means it's the same as this, right? So you have to put in one of the middle pieces. So this counts. Go ahead and fill this in. Isomers have to have the same number of atoms, right? So let me see. Each carbon has 4 bonds. Let me fill in my hydrogens. A hydrogen here, a hydrogen here, 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 and here. Okay? So the rule is isomers must have the same molecular formula. My molecular formula on the first one has 5 carbons, 12 hydrogens. Let's check and see. 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. Okay, I have 5 carbons. I hope I have 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, yay, I have 12 hydrogens. All we're doing is connecting the same number of elements differently. We're just connecting the carbons differently, okay? So let me ask you this. I want you guys to participate in this process. How can I make my longest chain shorter so it's not 4 carbons anymore or 5 carbons? It's a different number. And if that's the case, where do I place the carbon that breaks off? What do y'all think? Anybody? How many carbons should my longest chain have for my next isomer? There's a logical sequence here, right? We went from 5 carbons to 4 carbons. What do you think the next one will have? Right. Okay, let's try 3. Okay, let's try 3. If we try 3, which carbon do we want to break off? You try to break off one of the end carbons, right? But you want to make sure you're not breaking it off to get what you had before. So here, I will label the carbons, carbon 1, 2, 3, 4. Let's call this carbon 5. So before this was carbon 1, 2, 3, 4, carbon 5. So 5 broke off and went on 2. Which break off this time? What do y'all think? Yeah, very good. You want to break off 4, right? So if we break off 4, I think I can convert this structure. Let's break off 4 right here. Oh, snap. Okay, I answered my question. I was gonna, sorry. I meant to ask you, then I answered the question. I'm gonna ask you, where do we put carbon 4? I kind of already pointed at it. Oh, well. So you want to put the carbon 4 right here. That 4th carbon that we broke off, you want it and all of its hydrogens to come right here. Okay, and then the hydrogen that was here goes where this carbon was. Do you see how different they look? Now, continuous chain has 3 carbons versus what we had before. And then we have attached the carbons that broke off. Okay, so 5 carbons that kind of messed up the 4 carbons to make it a 3 carbon, but you get the idea. So you're breaking off the end pieces and middle to make the more compact as you get different isomers. And these molecules are arranged differently. They will have different physical properties. They may even, one may be a gas, and the other one may be a liquid. They just act differently because of the arrangement of the atoms and the elements. Okay, so I just realized I need to fix this. So I'm going to put this back where it was. Carbon 4 was here. Carbon 4 was surrounded by 3 hydrogens. I'm going to fix this. Right? So from here, this is the one that has 4 carbons as the longest chain. The last one here will have 3 carbons with the longest chain. And then the top one is a carbon, the bottom one is a carbon. And you can see how the hydrogens are here. Let me draw my 4 bonds there, 4 bonds there. H, 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 like that. Okay? So yeah, that's the easiest way. I mean, are there different ways to do this? Yeah, there are different ways. But when you have a acyclic, the one that's kind of a chain compound, the easiest way is just to shorten it by one link each time or one carbon each time. These are not ornaments, but you know what I'm saying, but one carbon each time. Attach it on the side. Very good. Yes. Yes, the rule is very good. You're talking about your lab, huh? See, one, two, three, four, five. The number of carbons and the number of hydrogens have to be the same, or if they're not the same, they're not isomers. So when you're doing your lab, before you even try to do all this stuff, if you're comparing two compounds, count the number of elements. If they're different, they're not isomers at all. They're completely different compounds or molecules, right? Okay. Yeah, I know. Hey, you can ask questions about the lab. This is fair. Yeah, the lab does relate to what we're doing right now. Yeah. Okay. And so, Elizabeth, you had emailed me earlier about the skeletal structure. I saw this T-shirt online one time where they had drawn this structure like this, and it was supposed to be a Halloween thing, something like this, and it's like a skeletal model, and only the chemists were getting it, and even half of them weren't even laughing. They didn't think it was funny. I'm like, you know how Halloween has skeletons and stuff like that, so yeah. Some didn't think it was funny. I was like, this is so funny. I didn't buy the t-shirt, but I was like, this is so funny. They have a skeletal structure for Halloween. And the other ones were like, it's not that funny. Listen, it's their loss. When you teach this stuff, you gotta find the jokes where you can find them, man. It's hard to come by. So with the skeletal structure here, it's a little tough, but let me see if we can start with simple ones and then we'll go to these complex molecules. Once again, when I was learning this, I'm like, if one thing works, why do other things? As a student, I'm like, I don't want to learn something new. If something is working, why can't we just stick with that? But once again, the people that do this as their job and they're drawing a lot of molecules, it becomes tedious and they're like we still want to communicate but make less effort in drawing out all these structures. So that's when you have a skeletal structure, bare bone structure. With a skeletal structure, they're telling you here, assume that there are carbon atoms at the junction of any two lines, meaning that this junction right here has a carbon atom, and at the end this and this has carbon atoms. Assume that there are enough hydrogen around each carbon to give it four bonds. Okay, check. And then draw in all symbols of heteroatoms. So we will not draw the carbons and we won't draw the hydrogens. The carbons and the hydrogens are implied. So I'm going to say here, carbons and hydrogens are implied. Okay, so it's understood, it's there. We don't talk about it, it's there. Okay. But if you have a heteroatom, because the heteroatom can have so many different identities, the heteroatom can be a nitrogen or an oxygen or a sulfur or a fluorine. We don't know what it is, so we can't assume what it is, right? You have to actually write it out. And if there's a hydrogen attached to that, you can write it out too. Okay, so we have to write out heteroatoms. We can't assume it because it could be one of the many heteroatoms there are. So you draw the heteroatom and the hydrogens directly bonded to them. So let me start with simple ones, okay? I know they get to that one. Let's start with this even simpler one. Okay, so in the world of organic chemistry, which is where we are, this is a bond. No, it's not just a bond, it's a molecule, okay? Remember they said the end of each line is a carbon. So I'll put in a carbon right here, I'll put in a carbon right here. And then assume each carbon has enough hydrogens to make sure it has an octet. So each of these carbons have one bond, right? I need to fill in the three missing bonds, fill in the three missing bonds. And then at the end of each bond, I put in a hydrogen. So what started off as a line was actually ethane. Then when I did the V or upside down V, at the end of each line, you put a carbon And at the apex or the corner of two lines meeting, you put a carbon there too. And then fill in the missing bonds. So my carbons on the end each have one bond. They're missing three bonds, right? The one in the middle is attached to two bonds, so it's missing two bonds. Now each carbon has four bonds. Then fill in your hydrogens right there, right there. Right? So if I do this, then essentially what I'm drawing here is this is a carbon with three hydrogens. And of course, you fill in your lone pairs here and that bond there. Okay? So since we've practiced this, we're now going to go into the next slide. Remember, the heteroatoms have to be shown. Okay? So here we start from this end, right? This is 1, 2, 3, 4, 5, 6. So you're going to have a what? This is called a cyclohexane. You're going to draw a hexagon, right? That's how you say it. You're going to draw a hexagon, right? Because in the place of each carbon, when I was first learning how to do this, I was like, I'm not ready to go from here to here. No, that was scary for me. So I will put the C's here. Hey, this was my process. So I'll put the C's here, draw the lines, subtract the C's. I know it's weird. Or even if I drew the molecule straight like that, I didn't feel comfortable. So I'll put in the C's just so I can see that the C's are in the right place. So I have 1, 2, 3, 4, 5, 6. I have 1, 2, 3, 4, 5, 6. And you see how the hydrogens are here? The hydrogens are implied, the carbons are implied. So essentially the molecule on the left is the hexagon on the right. So this is cyclohexane. Like we said before, cyclo means it's a cyclic compound, as in the first atom attaches to the last one. Hex means 6 carbons. There's 6 carbons in this. Ane means that all the carbons are connected via single bonds. So carbon, carbon, single bond. So you have a cyclic compound made up of 6 carbons where all the carbons are connected via a single bond. Cyclohexane. Okay. See with this one here, of course, once again, we have 5 carbons. They make what looks like it was the pentagon. It looks like a little house. And then with the O and the H, you can't leave those out because if you leave those out, we won't really know what they are. So you have to actually draw the O and the H. But everything else here is assumed to be a carbon and then the necessary hydrogens to make each carbon an octet. Oh, the one you're talking about is this one here. The aromatic ring you're talking about. So, okay. So the aromatic ring is like this. Okay, it's drawn this way or it's drawn like this. Yeah, so it's a hexagon with a double bond. So kind of double, single, right? So it looks more like this structure right here, right? And this is called the aromatic. Now you think when they're saying it's aromatic because it smells nice? No, it has a strong smell. Does it smell nice? No, it's just very strong. It's not even like gasoline smell, just a strong, strong smell. Okay, so finally we're here at this one here. It says, convert each skeletal structure to a complete structure with all the carbons and the hydrogens drawn in. Add lone pairs to all the heteroatoms. Okay. Cyclooctane looks like the stop sign, right? So every corner is a carbon. 1, 2, 3, 4, 5, 6, 7, 8. It says cyclooctane. Oct is 8. Ane, right? So bring in the hydrogens. H. It's a weird shaped molecule. H. So I'm bringing in 2 hydrogens to each carbon. H. H. Oops, I forgot that one. H. So make sure in this cyclic form, that ring, each carbon is assigned 2 bonds. So it just needs 2 more bonds, right? Okay. Oh. So let's see. With these ones here, the ones on the side, they're good. The ones on the side, they're good. Oh, they said lone pairs. Okay, lone pairs. Dot dot. I guess that oxygen is missing is two lone pairs. Now, let's go ahead and look at the carbon on the geometric side, right? It's a carbon here, carbon here, carbon here, carbon here, carbon here, and a carbon here. Okay, let me label them. Carbon 1, 2, I'll number them 3, 4, 5, 6. So carbon 1, 3, and 4, they have a third bond, right? So they're just missing one bond over here with a hydrogen. This is just missing one bond. It's missing one bond. Carbon 2, 5, 6, they're missing two bonds. So I put an H here and an H here, right? Hopefully by the time we're done with this lesson, you're like, okay, we get it. Carbon has four bonds. But yeah, some of this stuff, you go from, oh my goodness, to, oh yeah, four bonds, carbon. Okay, so that's it. I filled in all the hydrogens and that's it. These ones here are good. They're not even skeletal anyway, so there's nothing we can do about that. Here, let's go to that. Once again, the places where the lines intersect are carbon, 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 carbon. Okay. It looks like each of them, 1, 2, 3, 4, 5, 6. It's missing one bond, right? So 1, 2, 3, 4, 5, 6. So H, 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 H. That's it. And this is called lindane. It's an insecticide. And this is menthol. See, if you like mentholated gum or flavors and ice cream, peppermint, spearmint, yeah, this is a chemical right here. Cyclooctane, I don't know what that one is. I can't think of a regular reference. Oh, yes, thank you. Did I miss that? See, thank you. I missed that. Thank you. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes, thank you. Yes, each of those chlorines need to have. I forgot the heteroatoms. Y'all are looking at it from fresh eyes. Me, I'm just like, next. Okay. But yeah, all those chlorines need lone pairs, right? We got the oxygen over here. Okay. So this one here, we're talking about ibuprofen. We all know about ibuprofen, painkiller, and then this one here, fentanyl, a narcotic pain reliever. I've heard of it, but yeah. So they want us to figure out how many hydrogens are bonded to each indicated carbon, carbon 1, 2, 5 in the following drugs. Okay. Yeah, all of these drugs are organic compounds. So people who want to major in making drugs have to major in chemistry, pharmacology, one of those things. Usually in pharmacology or pharmaceutical sciences, and they have to take a bunch of chemistry classes to know how to make these drugs. Okay, so our carbon number one is right here, right? So imagine the carbon is here. Carbon has to have four bonds. I see one here, two, three, four. Well, it doesn't need any additional bonds, so there's no hydrogen here. I don't have to draw anymore. This carbon here has one, two, three. It's missing a hydrogen, so I can draw a hydrogen here. I don't want to confuse it with a label, right? This is carbon one, carbon two, carbon 3, okay? So we're just looking at the carbons, right? Yeah, indicated carbon. Okay. We're looking at the carbon only. There's the carbon here is attached to one bond, one bond. So there are two bonds missing here. I can put the hydrogen here. Okay. Then carbon 4 is right here. This carbon has three bonds already. It's missing a fourth bond with a hydrogen. Where's carbon 5? Carbon 5 is right here. It's attached to two bonds. It's missing a bond and a hydrogen. Yeah. So hopefully this, I'm hoping that as you're seeing us walk through this, you're like, okay, you know what? I can do this on my own. You know, your homework and stuff like that. So you hope, and as you see the complexity of these molecules, now you can see why right about midnight, if you watch TV, I don't watch TV, I watch Netflix and other subscribed whatever. But when I used to watch a lot of TV, close to midnight, if your loved one was prescribed the following medication, please call this number. I'm like, oh, they have done it again. Because most of these analgesic, all these medications, anti-inflammatory, whatever, they have all these molecules, and we'll see later on, all these molecules here have these side effects, right? And so when you're putting it in your body, it's not that simple. As we go into functional groups. So since we started around 6-ish, I will stop at around, I know I'm looking at the slides here. We have a lot of slides to go around 7:30 because at some point I figure you guys will be burned out, right? And we can pick this again tomorrow. A functional group is an atom or group of atoms with characteristic chemical physical properties. So let's go back to 1405. I didn't even ask you guys if you took 1405 because I had a goal, so I was going straight for the goal. Okay. In 1405, if you had chemistry before this class, elements are arranged in the periodic table by groups, right? You have the group 1, you have group 2, and we have concluded that elements in the same group or family have similar characteristics. But now we're dealing with compounds, not elements. So do we see similar characteristics in compounds? The answer is yes. But what is similar about them? This is the functional group. So the functional group, these are essentially groups of similar, I should say group of elements, not really similar, but yeah, groups of elements that appear over and over again. Okay, so these tend to be groups of elements that appear over and over and over again in elements that are in the same family, okay, or group. And what that does is the elements that you see will essentially cause the chemical to have the same chemical or similar chemical and physical properties. Okay, a functional group can be made up of either heteroatom or multiple bonds or maybe both. For you guys, this class, we're trying to keep it simple. It's an introductory class, so we'll see mostly heteroatoms. So when you are asked to look for functional groups, the first thing you're looking for is a heteroatom. You're looking for a chlorine, a sulfur, an oxygen, and nitrogen. What else is there? Anything, fluorine, bromine, iodine, anything that is not carbon or hydrogen. You're roaming all over the compound, looking left to right, trying to find one of these. And that will kind of take you closer to the functional groups. If all of these are missing, you're looking for multiple bonds, the double bond or the triple bond. Okay? So the R is essentially the molecule, and then you have the functional group. One student one time said R is the rest of the molecule. So since then, I'm like, I like that. That's not what chemists call it, but we can call it whatever in this class. R is the rest of the molecule. So the functional group is that identifier group, and we will see it in all elements. Similar-ish, right, similar. The melting point and boiling point can also be influenced by the rest of the molecule because, very good question. I'm loving these questions, okay? Because you can have a group like, for example, let me look at a simple alcohol, CH3, and then it has one OH, and this OH is the functional group, and then you can have CH3, CH2, 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 CH2. I'm trying to make a point, CH2, then finally OH. Yeah, they have the same functional group, but the rest of the molecule for the second one is humongous. It's huge. Therefore, their melting points will both be high. This will have a high melting point, but this will be higher than the top one because there's so many carbons here. So same functional group have similar, but not same melting point. They will both have high melting points, right? But this will have an even higher melting point because you have all these other elements there, and it makes it heavier and higher, okay? So yeah, we're getting to all of that stuff, yeah. So remember, We're pretty much isolating the rest of the molecule and then the functional group here. And they're telling you here the rest of the molecule usually has a bunch of carbons and hydrogens, okay? So we're going to be looking at this. So we're now looking at hydrocarbons. I mentioned this earlier, right? And I've been talking to you guys about alkanes, alkenes, alkynes. We even mentioned aromatic at some point. These are all grouped together as hydrocarbons. Okay, remember hydrocarbons, these are organic compounds with carbon and hydrogen only. So they only have carbon and hydrogen, nothing else. It's carbon and hydrogen. They can have multiple bonds, but they only have carbon and hydrogen, many of them. So hydrocarbons are organic compounds that contain only carbon and hydrogen. Now, alkanes, we already mentioned this. The whole family of alkanes has thousands of compounds. They all have carbon-carbon single bond, meaning that the carbons are all connected via single bonds, whether it's 2 carbons, 4, or 1 million. They all have single bonds, carbon-carbon single bonds. And then it says here, technically, they don't have a functional group. They don't have anything special or unique that identifies them besides a lack of heteroatoms and multiple bonds. So alkanes are the simplest of all the organic compounds. The next one is alkenes, E-N-E-S. Alkenes have a carbon-carbon double bond. They have at least one carbon-carbon double bond. Okay, so when you have an alkene, you want your eyes to go straight to the carbon-carbon double bond, then you know for sure this is an alkene. Okay. And so with alkanes, by the way, their name will be some kind of prefix based on the number of carbons, and then they'll end with A-N-E. I'm trying to think, oh, octane, right? If you go to the gas station, you're trying to get some fuel, they say, oh, this fuel has got octane. I'm like, octane, octane, A-N-E. Oct means 8 carbons. That's an alkane they put into the fuel. They add it to the fuel as an additive to help prolong things, whatever. And then you have alkenes. Alkenes, once again, the name of alkenes will be some kind of prefix that has to do with the carbon, and it will end with E-N-E. Like we said, polythene bag. And I'm trying to think of an alkene that's common. Yeah, polythene bag is an alkene. If it ends with E-N-E, it's an alkene, most likely. Alkynes, we said, ethine or acetylene, YNE. Alkynes end with YNE. Once again, you have some prefix that tells the number of carbons and ends with YNE. Alkynes tend to have at least one triple bond. So at you guys' level, keep it simple, one triple bond. Okay. Aromatic compounds always have this aromatic group. It's called a benzene ring. Benzene looks like this. It's a hexagon, a 6-membered carbon ring, or yeah, a 6-membered ring. It's called a ring, but it's a geometric figure, right? And then it has 3 alternating double bonds. So double bond here, single bond, double bond, and this is called the benzene ring. When they say ring, they don't mean round. They mean a geometric figure. Okay? Benzene ring. So here, these right here are the functional group. We just saw alkane. We see alkene. We see alkyne. There, there, there. And of course, we have examples. This one here has no double bond, all single bonds. This one here has a double bond. Oh, the one thing I want to mention here, since they chose molecules, at least the first 3 that have 2 carbons, look at this one here. Let me draw the Lewis structure so you can see. The Lewis structure has the carbon on the left having 3 hydrogens, right? Carbon on the right having 3 hydrogens right here, like that. You see that? This one here, because it has a double bond, is missing 1 hydrogen. So one of the things you can see, once again, there's a lot of trends. It's like every time you're looking at it, ask yourself, what is different? It has a double bond, but it has 1 less hydrogen, right? This one here has triple bonds and it has 2 less hydrogens. So the formula for this first one is 2 carbons, C2, 1, 2, 3, 4, 5, 6. Oops, 6 hydrogens, H6. Second one, C2, 1, 2, 3, 4, H4. It has 2 less hydrogens. Third one, C2H2. So as you're bringing in a second bond, there's less, right? So hopefully you see the trend. I really have to covering everything generically, right? I'm not picking and choosing things. So depending on what you're working on, you may have this or you may not even notice this later on. And then of course you have the benzene ring right here, and then they have the model right there. So the identifier is the functional group. For the alkane, it's just a carbon-carbon single bond. I know they say there's nothing, but the carbon-carbon single bond throughout is the identifier of the alkane. For the alkene, it's the carbon-carbon double bond. So this is in your lab work, right? The alkyne is the carbon-carbon triple bond. For the benzene, is that once we're dealing with the benzene, right? Time. So I'm going to just go through the functional groups and then I'll end there. With this group, alkyl halide. Halide is elements. Since you guys have your notes with you, just, write this down. I know it's written on here. Write it down. Halide. So with this one here, you have the rest of the molecule and you have either fluorine, chlorine, bromine, iodine, one of those. They gave you an example here. See that one? This part here on the left was like an alkane, right? But instead of having a carbon on the right, you have a bromine. So the bromine here tells you that's the functional group. Remember, you're looking for either a heteroatom, or you're looking for multiple bonds. Alcohol. Alcohol is the rest of the molecule and then OH. So OH is alcohol. Okay? Now, remember, water is H2O, right? The Lewis structure for water is HOH, like that. But the alcohol is an organic compound. It has to have a carbon. So we cannot argue that, hey, water is really alcohol because there's no carbon in water. That's not a valid argument. You have to have the carbon and then the OH to make it an alcohol. Okay? And then, so let's think about alcohol. You have drinking alcohol, right? Rubbing alcohol. What else? The alcohol in gum, sugar alcohols, xylitol, many other alcohols, right? And then ether. I'm trying to think, where is ether used? I feel like I've seen movies where they use ether to knock people out. I watch mystery movies, so it's not like, some crazy movie, just mystery movies where they knock somebody out using ether. But yeah, so with the ether, the functional group right here is in the middle. So you have a carbon. You're looking for this combination, a carbon, an oxygen, and a carbon. So actually, while I was working on this, I just thought about something I need to do to kind of add to this to help you guys figure out the functional groups. Let me see. 27. Where's 27? Added page here. Wait, is this adding to the right thing? Hold on. I feel like I'm not adding to the right thing. Okay, added page there. Give me just a moment. I'm for some reason I'm just struggling to get this. Oh, I'm adding to the wrong place. Okay, this is fine here. This is fine. Okay, so with this one here, with the heteroatom, I'll say here with the alkyl halide, what you're looking for, so you are looking for this in your structure, looking for a bond between a carbon and a chlorine, or a bond between a carbon and a fluorine, or a bond between a carbon and an iodine. What else do we have? Or a bond between a carbon and a bromine. So you're looking for this bond, this direct connection right here. And when you identify that connection, then you know you have an alkyl halide. Okay? I'm trying to break it down to fundamental level so it's easier for you guys to find it versus just reading the slides, right? For the alcohol, what you're looking for, when they say find an alcohol, this is the combination of bonds that you're looking for. You're looking for a carbon attached to an oxygen and a hydrogen like this, or it can be written out like this. A carbon attached to an oxygen, and then the oxygen attached to a hydrogen. So these, of course, will have lone pair here. You're looking for either one of these combinations, and this is called an alcohol. I know we have the rest of the molecule out here, and you may have other things going on, but you're looking for that combination of bonds, right? And then for the ether, you're looking for a carbon attached to an oxygen and then to a carbon. So you're looking for COC. Okay, so hopefully this will make it easier. For an ether, you're looking for this combination, a carbon attached to an oxygen attached to a carbon, like that. So COC. And when you find that combination of bonds, you have an ether. If you're not seeing this combination of bonds, you don't have an ether. Okay, so COH, alcohol, COC, ether. Let me see. With the amine, you're looking for a carbon attached to a nitrogen. Okay, so a carbon directly attached to nitrogen, and then you have other things going on here, and that would be the amine. So what I'm going to do here is, let's see, we have a couple more to go. Oh, I'm glad we have this one here. So, okay, for real, I'll say start here. This would be my starting point. I do feel a lot better. We've made some progress in the slides. So for this one here, they say identify the functional group in each compound. Some compounds contain more than one functional group. What do you think the functional group is in this first one? I see the name, so I'm like, well, come on now. Okay, let me highlight what I'm looking at. I see my heteroatom, right? And I see an oxygen, and the oxygen is attached to hydrogen from this top end and attached to a carbon from the bottom end. So essentially COH, this is alcohol. Okay, alcohols tend to end with all. Isopropyl alcohol, or what is it called? Ethanol. They tend to end with all. Xylitol, things like that. This one here, let me find my heteroatom. I see a nitrogen here. I see a nitrogen here. Now, if I were to draw this out, there is nitrogen, 1, 2, 3, 4, and then this one here. So I'm going to draw this out real quick. 3, 4. The nitrogen. The nitrogen is attached to a H and an H here, an H and an H here. And I just told you a carbon attached to a nitrogen is an amine. Very good. Right? So that's pretty much it, an amine. So if you smell the odor of rotting fish, that's what this chemical is. Amines do not smell very great. You know how what's it called? The glass cleaner? What's the glass cleaner called again? The glass cleaner. Windex, yeah. Windex. It has amine in it. That's why it smells like pee. And pee has amine in it. That's why it smells like that. So anyway, that smell is the amine smell. Okay. Oh, look at this one here. Styrene. Polystyrene. Okay. Styrene. This is the stuff that's used to make styrofoam, right? And styrofoam is essentially polystyrene, many of these. Okay. So what's the first obvious functional group we see here? I see two. I see this one. And I see this one. Yes, you have your aromatic here. Aromatic or benzene, right? And then we have our double bond here, alkene, right? So yeah, if you look for the combination, it's really not that bad. You see how that wasn't that bad? Same here, functional group, obvious, that one, right? Alkene. This one here, OH, alcohol. And then, oh, I didn't do this one yet. I didn't do this one here. Because this is not the one that's COC. Because in the COC that I gave you guys earlier, the bonds on the oxygen are spread out. They're not together. So this is not an ether. This is actually a ketone where it looks like this. This is what the situation is. So this is technically a ketone. I just realized we haven't covered that, but we'll cover it when we meet. Okay, guys, it's a lot. I want you guys to, take a little break and then you can go ahead and do your homework as you go over the part that we've covered. So, can you guys meet again tomorrow this time? We can't finish all of this tonight because you right now I feel like you're already saturated. Okay, great. So we have a group. The rest can join us if they want to. If not, I'll record this and I'll post it. And so, okay, real quick before I go, the goal is to post this on. Let's see. Let me see. Oh, you're welcome. I'm glad you guys came. Yeah, I'm glad you guys came. So the first one I posted, where did I post it? Okay, I don't remember where I posted it. I think the video was here, right? For the first one. I put the video in here. Yeah, that's the one where I recorded the video, but it came out as a document. Okay. So let me see where I did do the ionic one, and I think I put that in here, right? So the video I did for chapter 3 is in here. I did chapter 4 today before I met with you guys, so I'm going to put that as part of the lecture. So when you look at the PowerPoint, it should be on there as collaborate chapter whatever. Since I'm doing this in 2 parts, I'm going to put chapter 10 part 1. Okay? Any questions? Okay. Yeah, meet each other. This is great.